general optimization problems, like you can come up with any optimization problem. You can come up with optimization problem like this, max or min. You can come up with more complicated as well. So in general, they are difficult to solve. So either, like, depending on case, they may not find the best solution, as I described, if it's the non-convex problem, or basically they have a long computation times. And in this case, we try to basically formulate the problems in a way that they obey the certain criteria or certain optimization problem types. For instance, one example is least square. So in least square, basically we have the, as you see in this case, you may have seen this from the other courses as well. So for different measurements, matrix A, we have different variables AX, and we try to explain the variables B. So for instance, in this case, let's say A is m times n. There are n variables. This is n times 1, AX, and this is m times 1. So for instance, for x variables, we have taken m measurements, and we try to find optimal values for the x variables. And in this case, in least square, what does it basically? It tries to minimize the second norm, square of the second norm of the difference between them. And it minimizes the variable x, given that ax base, second norm, and square. And in this case, basically this is same as axb square transpose axb. And since this will be minimized, we can take the first derivative. And when we take its first derivative, we can come up with the closed form solution. And the closed form solution here will be A transpose A inverse times A transpose B. And in this case, this can be invertible because this is a square matrix. As long as the matrix is basically A matrix, it doesn't have duplicates, this will be inverted. And the solution will be A transpose A minus 1, A transpose B. And this will be the solution. And again, one thing about this least square is easy to recognize. So in many cases, so whenever you have multiple measurements with variable x equals b, then this is a least square problem. And then solution is, as I described here, is a closed form solution. So there are other problems as well, which we'll use in this course a lot. One is a linear programming problem. So linear programming problem will be used a lot in this course. So in linear programming problems, so we are solving the linear programming problems, but there is no closed form solution. However, the algorithm that exists are basically find you the optimal solution. So linear programming problems are convex. That's why the optimal solution we find via the algorithms are global optimal solution. Global optimal solution. And again, the LP is not as easy to recognize as least square problems, but the problems can be formulated as LP by using certain tricks. So in this case, C is basically a vector. So in this case, let's assume that C is n times 1 vector of coefficients. X is basically n times 1. And in this case, for different, we have m constraints. And in this case, we have values given at A, and they should be smaller than B. And as you notice, this expression is linear in terms of the x, and the constraints are also linear in terms of x. Since both objective function and constraints are linear in terms of x, that's why the problem is called a linear programming problem. And again, the variables we'll optimize are here, which are the x values here. And another thing is convex optimization. So in convex optimization, so we have this minimize f0x. So in this case, f0x doesn't need to be a general, but this needs to be a convex expression. And f0x the f0x, the objective function is a convex expression, and the constraints f1x, f2x up to the fmx, as you see here, are also convex expression. And they are smaller than bi. And again, the variable here, we used ix here, and we try to minimize x in this f0x given the constraints, the convex constraints fix, where I is from 1 up to the m. And again, there is no closed form solution. These problems are more complicated to come up with a closed form formula. But again, the algorithms are quite efficient, so you can come up with any solver. So for instance, there are solvers like CVX is a well-known solver. And in Python, for instance, there is a version of CVX called CVX-Pi. And in this case, CVX-Pi is basically a good solver, and you can solve convex optimization problem, linear programming problems, and other type of problems efficiently by using this solver. And again, compared to the least square problems and linear programming problems, convex optimization problems are more difficult to recognize. And in this case, there are many tricks to transform the problems into the convex form.